Thank you. Good morning. I will need. So this will be the second lecture, and I will start with a very brief reminder of what was discussed last time, yesterday. So yesterday we started with the classical transport in normal metals, and there were two basic equations. One is the diffusion equation. With this, then by t minus square times equals 0. This is the diffusion equation that you can apply not just to metals, to any kind of gas that propagates in medium diffusion. And second, relations. So and for this equation, we said that there is an object called the diffusion, which is the propagator of this equation. D of Q and omega is 1 over dq squared minus omega, and d here is the diffusion constant for metals is Fermi velocity squared times tau divided by the dimensionality. And the second relation was the Einstein relation that relates the electrical conductivity to the diffusion constant. With mu k is the tensor states, the derivative of the concentration with respect to the chemical potential. And this is, as I explained, this is a very general relation that applies to any material, and in a particular case, when you have a metal which is modeled by the parabolic spectrum, from here you can derive the Joule formula of conductivity, which is E squared concentration times tau divided by mass. And from this equation, you immediately see that it's very specific because it contains mass, and mass is defined only for parabolic spectrum. Very good. So, just one other comment about this equation. In the metal with the parabolic spectrum, you have Fermi surface, Fermi level with some energy, all states appear here. And this equation for Joule, it contains mass, which is the curvature of the spectrum, and it contains the total density n, which means the total number of field states. Whereas this equation for conductivity contains two parameters, mu and d, which only know about what happens near the Fermi energy. This is the density of states at the Fermi level, so it knows how many states you have on the Fermi surface, near the Fermi surface. And the diffusion constant knows only about Fermi velocity, which is the velocity here also in the Fermi energy. So if you had not a parabolic spectrum, but some more complicated spectrum, but still chemical potential is quantified from the surface, you can apply this equation, but you cannot apply the second. Okay, so this is what happened on the first lecture, and then we started to discuss the quantum description of the metal, and quantum description, again, this is a repetition of what was yesterday. This quantum description is usually done in terms of the Green function. Green function is, by definition, can be retarded or advanced, and it's just the inverse operator, energy energy plus or minus I0 minus Hamiltonian. So I will, okay, let's let me do it. Full Hamiltonian, this thing inverse is the wave function plus or minus I0 corresponds to the target advance. The Hamiltonian was, as we discussed, has a part that depends on momentum and corresponds to the dispersion relation like that, plus potential that is random and that corresponds to impedance. So this is usually called disorder potential. And for this disorder potential, we had the Gaussian distribution, so V on average is 0, and it has Gaussian distribution, so it is fully determined by the second moment. The second moment is just a delta function with a coefficient that contains parameter tau. So the stronger is your disorder, the smaller is tau. Yeah, and once again, the reminder from here, whenever we're talking about the metal, we always assume that the Fermi energy times tau is large, or same thing, Fermi momentum times mu pi is also large. So the first goal was to average such a wave function with respect to distribution of the disorder, and the average wave function was written in a diagrammatic way as the function which contains some self-energy. So it equals 1 over epsilon minus psi of p minus sigma. And sigma is a set of diagrams starting with this simplest diagram. So the dashed line is just this correlator, this delta function. Then next term is this thing plus cross diagram and so on.
When we complete the diagrams, the initial part before we introduce sigma, okay?
Yeah.
We had a Taylor expansion in terms of the strength of spheres. Then we recombine the diagrams, right? And then we calculate like sigma up to some order, and then combine G using this sigma, right?
Yeah.
But at that moment, when we combine G, we like do it to much bigger order because we like take into account a lot of diagrams. Yes.
You mean this here?
Yes. So it formally takes into account diagrams with much higher order in perturbation than we actually like calculate.
Yeah, I got a question. So actually, this is a very typical situation. It happens almost always when you do a diagrammatic expansion. And the reason for this is that a single grid function without sigma has a singularity at the Fermi surface. When epsilon and psi are 0, it is divergent. So in the diagram which contains two grid functions, three grid functions, all at the same momentum, because it's the external moment, these singularities multiply and become stronger and stronger. That's why you have to sum up this whole series. And the result is that you get sigma in the denominator, which actually removes the singularity. When you're at the Fermi surface and these two things are 0, your grid function is no longer divergent.
generally speaking, we take into account a lot of Taylor expansion terms, and we just take some random of them. Not all.
No, not random. We pick on the most divergent.
Ah, okay. Okay, thank you. I got the point. So like all those like non-reducible diagrams, they are like the most divergent diagrams.
It's reducible diagrams.
Yes, sorry, non-reducible. They are in some sense the most divergent. Okay, thank you. I got the point now.
Maybe before.
Yeah.
So could we see that sigma, the real sigma contains all diagram, and sigma is correction to the condition of flow, and we calculate sigma is up to some accuracy. So we sum up all diagrams to calculate sigma with some accuracy.
Yeah, that's exactly what we're doing. So, right, so actually the perturbation theory, as Josh just mentioned, is the perturbation theory for sigma, not for the mean functions. Sigma has the first order term, second order terms, third order terms, and what we also did last time, we calculated this first diagram, which corresponds to the Born approximation. And we found that it is equal to some real part, which is formally divergent, but has no physical meaning. It just shifts the position of the chemical potential, and the imaginary part was minus or plus I over 2 tau, depending on whether we consider target or advanced function, and this tau comes from this dash. So the next thing we are going to do
is a question.
Yeah. That was.
We're basically the strength of our positive tau, right?
Yeah. Well, actually, tau has a dimension, so the actual parameter is this product. If further times tau is large, which means the inverse of tau is small. So the next thing we are going to do, if there are no further questions, we will consider these two diagrams. And so they are of the next order, but there is one additional interesting thing about these diagrams, namely, let me just draw them separate. So this is the first one, and we have some external momentum P that enters from here, and the same momentum going out from there. Each dashed line is a delta function, which means it's just one in the momentum representation, so it's just a number, but also means that any momentum can go along this dashed line. So inside we have some other momentum P1 in this line, some other momentum P2 in this line, and then again P1 here. And so this object, to compute it, we have to multiply three bin functions like this and integrate over P1 and P2. Now if I draw the second diagram, which crosses like this, we have external momentum here again, the same P. So here, I have P1 in this line, and now I can call this line P2. Yeah.
Excuse me, if you want to write out what this corresponds to, what do you mean by there can be any momentum going along the dash line? So I don't yet really see how to implement the diagrammatic rules.
I will write it at the beginning. I want just to finish this thing that the momentum in this middle line is P1 plus P2 minus P. So, to answer your question, I can write this diagram explicitly. It has two dashed lines, which means 1 over 2 pi mu tau squared. And then there is an integral over P1 and P2, and three green functions, 1, 2, 3, epsilon minus sine P1, say, also squared, epsilon minus psi of 2 plus or minus. So basically, this is the expression that corresponds to. So we have the functions of momentum p, p1, and p2, and this dashed line, I can say that we have a momentum p entering here, and momentum p1 going out here, so there is a momentum p minus p1 that propagates along the dish. And there is a conservation of momentum. And then there is another line, and the momentum here is p1 minus p2. Then when this momentum comes back, p1 minus p2 plus p2 becomes again p1. And then when this momentum comes back again, p minus p1 plus p1 becomes p and p goes on. Well, actually, you can do this. I don't want to really spend time more on this topic, but you can do it like this. You have green functions and you have some operators, and you can write it in real space representation. The green function between points and v at corresponding points. Then you have a dot function. You have to do a Fourier transform to momentum representation. Then you will see that integration or position of this point gives you the conservation of momentum. So in momentum representation, all momentum come in the coordinate from this point should sum up to 0.
Don't you need 1 over 2 pi to the power of d for each momentum integration? That's one.
Yeah, the only thing I wanted to, why I draw these two things here is to explain what possible values of momentum contributed to this diagrams. You can think of it in different ways. Now, imagine this is your firm surface. So this is momentum space, yes, phi. And you have all the states with small momentum field, and up to this sort of sphere dimension. And P is the momentum of the external particle somewhere at the further surface. This is P. Then you scatter on the first point, and you go to some position P1. So it's just like the particle goes to the momentum P, then it is scattered at the impurity, and the momentum changes, it becomes P1. And then it scatters again, and becomes P2, and then we go back the same way, so we this. So in real space, you have 1 point, then a second point, and then this dash line is a dot function. So it means in real space, you have to return to the same point, and then return back to the first point. It's not a very good representation because I have crosses in real space and momentum in momentum space. This is the process that corresponds to this diagram. For this diagram, you also have two processes, not just going to this schedule here, then we go here, then we go back, then we go here, then so you schedule on the first, then on the second, then again on the first, and again on the second. Well, any questions to this point? Okay, I will not calculate these diagrams, I just wanted to say that, as I already mentioned, answering the previous question by some people from the audience, the green function is very singular. It diverges at the further surface with both epsilon and psi of 0. And for this first diagram, we have inside two green functions of the same momentum p1, which means that when this p1, when this psi of p1 is 0, then this p1 is on the further surface, we have a singularity squared. And independently, integrating over p2, we can also have this function singular. While for this diagram, we can make the first function singular, put in p1 on the further surface, last function, if it was, for instance, is also singular, but this middle one appears somewhere. It's not necessarily on the first space. This combination of 1 plus 2 minus p can be anywhere. Therefore, the first diagram actually is much larger than the second diagram. Just because in integrating momentum space, we can pick up the larger integrand here, and this much larger, if you analyze it further, it's much larger in this parameter. So if Fermi-tau is large, it means this diagram, I don't remember exactly, if Fermi-tau is larger than this Fermi-tau is. And this is actually a very general situation. You can do the same calculation for diagrams with more lines, and you will see that whenever the two dashed lines cross each other, the diagram becomes smaller compared to the same diagram without such crossing. So there is a very important, so again, using our small parameter, there is a very important observation that we can effectively calculate the average string function taken into account only for the scope of non-crossing diagrams. Non-crossing diagrams where the dashed lines do not cross each other, give the main contribution. And turns out quite easy to solve all such diagrams.
Sorry.
Again,
There was a question somewhere.
yeah.
Small our parameter and how small mean another order.
Yeah.
Power.
No, it's some power.
So we can only, so for example, like we have other diagrams, we will have to count crossing diagrams at some point to get
We will get to this point later.
Yeah, sorry, and another question. I just want to have some kind of classification of small parameters we use. So first of all, we made an extension that's disorder, and the formal parameter was again like epsilon tau, or
Well, in the sense, if you like, we take the whole series, so it's an expansion, but it's not necessarily a small parameter because it's some everything.
okay.
And when we consider self-energy, yes, this diagram is larger than this because just it has an extra line, it's extra Fermi-tau. And these two diagrams compared to each other, it's also Fermi-tau. But you will see, so actually our ultimate goal is to sum all the diagrams completely, every diagram. We will just do it in steps. So.
I mean, it is just a little bit weird then that we considered like second order, and it turned out that in the second order there is some like third order diagram. I mean, we come to second order, right? And we stated that this crossing diagram is smaller by a factor of epsilon tau once again. Yes. So it is like, it should be somewhere in the third order, right?
Well, first of all, it's not exactly Fermi-tau, I believe the Fermi-tau squared. So it should be compared to the fourth order. But as I said, eventually we will sum all the diagrams. So it will not be a problem. We will just do it step by step, selecting first some smaller set of diagrams and then looking what happens if we get extra diagrams. So the idea of this summing this non-crossing diagram has a name, it's called self-consistent non-approximation. So it's also like a Borel approximation, but it's not easy. So in the Borel approximation, we had sigma, which is given just by a single diagram, green function, simple dash. Self-consistent Borel approximation means that now we will insert here inside this self-energy not the clean green function, but the green function that takes this order into account, where the average green function. So this is the average function inside sigma.
This is the same as the non-crossing.
Yes. Yes. So there is a non-crossing approximation, and the way to sum up all non-crossing diagrams is called self-consistent Borel. It's just a synonym. So if we say that sigma contains inside the average green function, what does it mean? Well, very simple. If this function is also averaged, it means that this diagram is also taken into account, because this dashed line, with the line here, is the part of the average green function. And if you say that sigma is like this, and then average G is itself G inverse minus sigma inverse. So it's this series expansion here. You will. So these two equations completely determine both the average G and sigma. This is G.
And also the zero. G not.
Yeah. So these two equations for two unknown things, for sigma and for average G, these are the self-consistent Borel approximations, and G should be. So we find sigma, we find average G with a sigma, and then we reinsert this average G back to compute sigma itself. So if you write out all these diagrams, you will see that indeed this sigma contains a simple Born diagram plus a diagram where this G inside has another sigma plus, for instance, a diagram with two such things inside plus diagram where it's 3 times one inside and so on. So it indeed sums up all diagrams without crossing the period. And it's actually quite easy to do because that's why this equation is sigma is 1 over 2 pi tau integral over all delta divided by pi over t. And then the green function that we have here is epsilon minus 7e minus the same t. So this is the self-consistency equation. Sigma is on the left-hand side and also inside the integral. So if we can find sigma that satisfies this equation, it will automatically contain all the diagrams. And from the Borel approximation, we know that sigma is just some imaginary shift, some imaginary number. It's independent of momentum. And actually, this sigma will be also independent of momentum because we have this dash line over covering everything. So this is a delta function. So in real space, it's a single point. It's a local object. It does not depend on momentum. So sigma is just a number. Therefore, this equation, we should find the number of sigma, and it actually turns out that it is exactly the same as it was with the simple Borel approximation. Just because this imaginary part is the residue at the pole, and the only thing changed is that we shifted this pole from it was very close to the real axis, now it's shifted by a finite amount, but the residue remains the same.
Yeah, absolutely confused. So, I look at a set of diagrams, and instead of the first diagram,
Actually, I already answered this question before.
Sorry.
We do not compute all the diagrams, we compute only a subset of diagrams. At this point, which is called self-consistent form, this subset of diagrams are the diagrams without process.
Okay.
It doesn't mean that the diagrams we thrown away are smaller than everywhere stuff.
Okay.
But this subset, it contains all the leading terms anyway, and the sub-leading terms might be not fully correct, but we will consider them later. As I said, we are going to include all the diagrams, not the terms.
Why do you know this kind of way, the function or?
You might do the
I mean, the sum, the direct sum, that only have non-crossing diagrams, that we have, say, you do not do the same way.
What are the same way?
I mean, you see, you have sum of non-crossing diagrams, so I would expect you would denote it in a different way, but you have this sigma there, right?
So sigma is actually the full self-energy, contains all the diagrams, also this diagram. But then I do some approximation. I can calculate the sigma approximately.
Okay.
And there are different approximations. Once again, there is a Born approximation, which has the single diagram. Then there is a self-consistent Born approximation that adds to the single diagram all non-crossing diagrams. And then, sometime later, it will be even more diagrams.
Okay.
Okay, I got the point of the answer. Okay, so this is an approximation, right? And we calculated the subset of all the diagrams. So this is like an approximation of the real result. Okay, so the question is, this is an approximation in what kind of small parameter?
You can guess we have only one small problem.
Okay.
Look, that's actually not so easy to see because
Yes.
each dash line has one on the top. So it looks like each dash line should share another small pressure. But we also have the integration of a momentum, which can be convergent. So it's not true that, for example, this diagram is not actually smaller than this one. It's the same reason why we don't take just this, but have to add up sigma many times, because each time we have a new sigma, we have a new singularity as well. So actually these two diagrams are the same one.
Okay. I got the point.
But
That is just
okay.
So I understand perfectly that formally what we call self-consistent Born approximation. So first equality is from zeta to next, like exact, yes, in some sense.
Well, it's what is called the self-consistent.
So this is.
So it's not exactly. We say that we want to include in the sigma only the diagram.
I mean.
And this means that you can insert this.
Okay. And it is correspond to like 3 levels diagrams.
Yes.
So,
Just to put another point here, we had originally a Born approximation which produces the imaginary particle I over 2 tau. It corresponds to the first diagram. Now we add up all these diagrams, and the result is the same. It somehow tells you that
The same tau.
it's the same tau, yeah. So in many cases, people wouldn't bother and just do Born approximation to get the correct result. Actually, it's not always the case. Sometimes the self-consistent Born approximation gives you a different result from a simple Born approximation. And this happens, I can tell you when. This happens when the density of states is not constant. So in our metal that we consider, we have a big firm surface, and we replace momentum integration with integration of oxide with some constant density of states. If the density of states, so we replace this by integral over psi, the same formula, d minus psi minus sigma. So if this mu is a constant, then you always get the same number. But if nu is itself dependent on momentum, so if you take into account the curvature of the spectrum, then the result will be different.
If impurities are non-local, that's also different for. If impurity is non-local, that's also different for what?
If impurities are not local, then stigma will depend on momentum. So this, you still can do some consistent model, but now this becomes a function of equations. Sigma is a function of P. Sigma becomes a function of P, and again, it doesn't have any simple solution, but for any particular spectrum, any particular form of impurities, it's still can solve it. Okay, so just to summarize this part, we found that the diagonals of cross impurity lines have some extra smallness, and we can neglect them for now. And if we neglect them, then we can sum from other diagrams. If you like, you can call it a three-level calculation or non-cross approximation or some consistent Born approximation. And the result is sequence given here. It's just I over k tau, and the average green function is the target response is just epsilon minus psi p plus or minus I equal to. So with this thing we can proceed further and a second word. So we proceed further and so what we compute next is the diffusion propagator that we had from the previous lecture, the propagator of the diffusion equation. We will compute it using green functions. And the basic thing is start is called the Cooper formula. Actually, it's quite a tricky topic, which I don't want to go into, how this Cooper formula is derived. It's some part of quantum mechanics, which is described in the textbooks, and it's a very general thing. I will just give you, without derivation, Cooper formula for the diffusion propagator. The diffusion propagator, the one that I already released, is the following thing. It's 1 over 2 pi mu average product of two green functions. Green function, the target green function, energy and momentum. Energy plus omega and momentum plus q times the advanced green function of epsilon p integrated over all momentum. So this is an equation which I will not derive, but will actually it's a very general thing. Whatever you measure can be always expressed in terms of green functions.
Is it also integrated over energies?
No, it's not integrated over energy. That's why I really don't like to do it.
So once again, D is this is the definition.
No, this is Hooker formula.
Yes, okay. I mean, the D is what?
This is the propagator of the diffusion equation, the one that we discussed.
Yes, okay, that's okay.
Well, again, I have removed some extra things here. So originally there was an integration of energy, and the propagator was defined differently, but for our purposes, this simplified version will be enough.
So don't you calculate for energy also?
No.
Right. And energy is kind of energy.
Energy actually, energy is epsilon, it can be anything, but it will drop out from the result. So once you integrate over momentum, the result is not dependent on epsilon. It's the trick. Okay, so this thing can be represented like this. We have a print function, the return print function goes one way, and then we have one print function that goes back, and we have frequency and momentum entering from left and exiting from right. So this retarded function has the momentum q times larger and the energy q times larger, and it should be averaged over this also. So the first thing to do, how do we average a product of two functions? First thing we do, we just multiply two average functions. So we replace average HR, average GA. This object I will denote by B. So B is, it's my definition of what B is the integral over all momenta of the product of average GR of epsilon plus n times average GA. Epsilon. And as before, instead of integrating over momentum, I will write it as the integral over sine of the variable, and my two average Green function give me epsilon plus omega minus, oh, okay, sorry, that was too fast. That remain d by d minus sine of p plus q plus I over 2 tau. This is the Carter function, it is plus. And the second one is advanced, is epsilon minus sine of p minus I over 2 tau. So we should integrate it over p, and p enters both here and here. And as I already mentioned previously, when we integrate, for example, a single Green function, it has a singularity near the Fermi surface, so we replace p integration by psi integration, which is valid near the Fermi surface. Now we have two such denominators, and they are shifted by the momentum q, which means that one Green function becomes as maximum at the Fermi surface, and the second one is the maximum at the Fermi surface, which is shifted by q. So these are two centers. This is the vector q. And I will not do this integration exactly. I will assume additional. I will make additional assumption that q is small. So vector q is small compared to Fermi momentum. So this shift is small compared to the radius of the Fermi surface. Yeah.
Physically, you just said we only consider low energy excitation about different
Well, actually, it's, yeah, okay. This is true. It's a bit more to the state that we consider low energy excitations. And since Q is much smaller than Fermi momentum, we have here P plus Q. P is of the order of the momentum, Q is a small fraction. So we can expand this function psi in powers of Q. And this expansion means that I can write minus psi over P minus P Fermi times Q. This is the scale product of the vectors. These two things instead of single psi. And now, since I have single out psi of P here and here, now I can say that instead of integrating over P, I will integrate over this psi. And this is a simple integral. Again, you just complete the integration contour and take a residue, and the result is here B equals 2 pi mu tau divided by 1 plus I tau P Fermi times Q minus I tau times omega. And this thing should be averaged over the whole Fermi surface, over the directions the Fermi goes. And already here you see that this does not depend on epsilon.
I'm guessing from the result looks, we still use the approximation that Q is small, but computational, otherwise we would have something like nu per energy minus nu per
Of course. Q is small and nu is constant. And the only thing we do, we take the residual psi. So we have one pole in the upper half plane, the other one in the lower half plane. You can complete the contour any way you like, the result is the same, and epsilon cancels because it's just a common real part of these two poles. Well, so this is still not the complete result, because now I will add another approximation which is more restricted to this. I will additionally assume that Q is much smaller than 1 over A, and omega is much smaller than 1 over tau. So I can say it's so small, Q and omega, that these two terms are smaller than 1.
Sorry, I still have some hard time understanding what are we actually calculating. I mean, from the beginning, we wrote down the equation, right? We found the function for the Hamiltonian, we derived the consultant system model approximation. After all, we found this like y great function, great, for this Hamiltonian. Now, where do we actually got the diffusion? Like, we hadn't thought about it.
So what we calculated before the consultant system model is the average green function. This thick green function is just means average result.
Yes.
Now, there is something which is called Kubo formula. Kubo formula relates the diffusion propagator to the green functions for any system. It's a very general formula, without any average. And what we want, so D is the product of these two green functions in general. Now I want to average this identity, of course. And then I have to apply this average to the product of the green functions. That is what I would right now do. Yeah.
Probably trying to say that it's not the diffusion propagator to density. And we will found the diffusion propagator.
This is exactly the point that I wanted to avoid. Diffusion, the propagator density is slightly different. It also involves energy integration. I don't want to do the energy integration. That's why I call it diffusion propagator, and this way, how I define it here, it will really be the diffusion, the difference. Any other questions?
Previous approximation about small Q kind of, I can see how we can derive it physically. Say the diffusion only measures on this kind of small scale. Is this approximation just something we want, or is this
Well,
also
actually, very good question. Actually, diffusion only has meaning on this scale. Because mean-free path is just the distance between two scatters. So to establish diffusion, you should scatter many times, which means you should go to a distance which is much larger than A, which means that momentum should be smaller than 1 over. And actually, there is an intermediate scale where momentum is smaller than Fermi momentum, but larger than this. It's called ballistic propagation. So there is a ballistic propagator versus diffusive. Yeah.
Is there any way to see that the diffusion, well, the diffusion is a quickly fluctuating quantity that can be averaged, and that's enough for all intents and purposes?
I'm not sure that I understood.
Well, this equation already implies that we average D itself over disorder. And as we know, like, it's not exactly true that a physical quantity is just average over disorder of some physical quantity in a disorder particular realization. It depends on the quantity. Is there a way to see that D is self-average?
To see this, you should go back to the previous question by Gosha and consider the propagator of test. That thing is well
I know this, I just want to see if there's any argument which allows easily to see that this particular quantity is self-averaging based on its, let's say, on expression for it or something like that.
Well, in a sense, I will answer this question in the next one.
Given what that is.
Much later than okay, so let's proceed. So these two things here, I now assume that they both, this tau times Fermi is just A. These two things are small branches to one that we have in front. So I can expand the powers of these two things. And what I get is 2 pi mu tau times 1 plus I tau omega and minus I. So this thing I should expand to the second order because the first order the average of Fermi is 0, average over all directions. So I expand it to the second order. And what I get is minus tau squared B Fermi times Q also squared and averaged over the directions of, does this fact have any significance? Now the average over the directions of the Fermi force. And since it's a scalar product, it's cosine of the angle on the side, this becomes B Fermi squared divided by the direction of the space. And what we recover here is exactly the diffusion constant, Fermi squared times tau divided by d. And so once again, this is 2 pi mu tau 1 plus I tau omega minus tau d q squared. This will be and it doesn't look like the diffusion propagator. And the reason why it does not look like the diffusion propagator is exactly because the average of the product of two plane functions is not the same as the product of two averages. So diffusion propagator, as it is written here, should be the following. It's product of two average green functions, like I just considered, plus the same product with the vertical dash line connecting the two functions, plus the same product with two vertical lines, and so on. Well, actually, I can also go across lines, but as I explained before, crossing dash lines always gives some slowness, so we now do non-crossing approximation, but in these non-crossing approximations, we should include all the diagrams like this. And the first term here is just my function b that I just computed. And the second term here is b squared. We have one pair of green functions, second pair of green functions, and we have a single dash line which gives 2 in tau. And the third diagram is the same as b cubed divided by 2 pi tau squared, and so on. So this is just a geometric series. You can sum it up, and what you get is tau times b divided by 2 pi tau minus b. Yep.
Let's see how the diagonal expansion is about, and how is it related to what we will have the average.
It goes like this. Originally, you have two green functions that are not averages. You insert, you do the expansion in this order, in V, and you have crosses that appear beside the any number. You can have any number of crosses above, any number of crosses below, and then you say that average in this product means that you should connect to process with a dashed line in all possible ways. And one possible way is like this. Connect these two, and connect these two. So this will become part of the average single green function. And this line I have to include explicitly because it's not part of the average green function. So if you do all possible things here without crossing dashed lines, they will all boil down to this series where each green function is also includes all the stuff from which is
So the single lines that you draw from the green functions are not actually single averages.
Yeah. For example, inside this V, I have the product of average. And the same goes for this all green functions are averaged separately. And on top of this, I also add this extra dash lines which connect out with the.
How do you get the power string?
This one?
Yeah.
This is power 1, power 2, power 3.
Okay.
I can put momentum, right? So we have P1 plus Q, P1, P1. And it's integrated over P1. And then the dash line can pass any momentum, so the next will be P2 plus Q, P2. And integral over P2 gives another value of P. So each dash line is a delta function in real space. It can provide transmit any momentum, so all momentum in these sections are decoupled and integrated separately.
For example, transfers momentum from top to bottom, then there will be less than Q1 on top, right? And you center line. And define that P2 plus 2 and P2.
Well, because I have momentum Q coming from here, and due to conservation of momentum, the same Q will be at every step. So I have this dash line, for example, that carries momentum Q1 minus Q2. does not depend on that.
Okay. Yeah, now there's like different directions on top line.
Yeah, actually, I had this table somewhere. Yeah, so this is what we have, and now you see why I want to do this expansion here. So I have 1 plus some small fraction, 1 plus small fraction, and here in the denominator 2 times 2 pi mu tau minus b, actually this 1 cancels out. So if I neglect only the q, I will get 0 in the denominator. And if I do not neglect them, what I get is this is exactly this. Oh, sorry. No, it's this one. So if you substitute b in here, in the denominator you will get d2 squared minus omega, and in the numerator actually you can take just 1 if you don't use this fraction. It's a small fraction. Okay, so this is a demonstration how a very simple diffusion equation with a very simple propagator can be derived from green functions. So it's just a very complicated way to derive a simple result. Are there any further questions? Let's check the question. What time should I finish?
I have 25 more minutes.
25 minutes. Great. Then, if this thing is this one doesn't move.
Yes.
Okay. So if there are no questions in that part, we go further and we will now derive one other classical result using real functions. Now it will be better than before. So the next thing is conductivity. Conductivity is also a very nice quantity that can be measured and computed, and hence it can be described with a Hoover formula. Conductivity, it's not a version of Hoover formula. Now, very similar to what we had with the field propagator, conductivity is 1 over 2 pi average of the following function. There's 2 green functions, just like before, retarded and impulse. And it has 2 current operators. Current here, and another current here. And if you apply electric field in x direction, and if you measure current on the x direction, it will be current operator over x. What the current operator is? Current operator is a vector which is electric charge times permeance. So just the velocity of the electron and the surface times its charge. So this is what electric current gets.
So where is the line to actually designate current?
Yes. Well, if you like, I can remove the paper line. There is just something here which represents the current. Yeah.
We here again say that we are interested in conductivity near Fermi surface, so we make an approximation of Q is zero.
This is what is called DC uniform conductivity. So Q is exactly 0, omega is exactly 0. Again, this is not the most general Cooper formula. There is another version which also takes into account Q and omega and has more than one type on the side. I just don't want to bother you with all these details. This one will be enough for what we need. Okay, so this calculation is easier than for the diffusion propagator. And actually it goes like this. We have 1 over 2 pi. And we have a single integral of, now I will just write it immediately as integral of psi. Two green functions, retarded and advanced, epsilon minus psi plus pi to 2 tau times epsilon minus psi minus pi over 2 tau. There's no omega, there's no q, it's just the same psi, the same epsilon. And in the numerator, I have a product of two velocity operators. Each one is like this. So I have E squared, D thermal squared, and I should divide it by D because I take only one component of velocity among D components. Okay, this is now a straightforward integral. You just completely contour on the side, up down doesn't matter, and you immediately get the following thing: E squared is E squared, mu is here, and all the rest, yeah, B thermal squared is also here, and all the rest give you tau divided by D. So 1 over D is also here, and tau is the residual. And this object here is the diffusion constant, so we immediately rederive the Einstein relation. So conductivity is E squared times mu times D. This is that much straightforward. Yeah.
Why we did not insert diffusion on the side?
You mean why we do not insert the level of dash lines?
Yeah.
That's very simple. Consider a diagram with just a single dash line. The new thing here is that we have these current operators, and they are actually vector operators. So we have, if we do it, we have one momentum here, one momentum here, and the integration over P1 will give 0 because it integrates over all directions on the thermal surface. So on average, the x component will be 0. If you like, we will have only one further velocity here in the numerator, and it's a vector. So we integrate over the whole thermal surface.
If you is unlocked, then it will not be 0.
Sorry?
If impurity is unlocked, then it will not be 0.
If impurity is not local, it will not be 0 because P1 and P2 will be now related. They will not be two independent integrations. This is the first thing, and the other is the next thing. You still can do this calculation, and if you have no local impurities, you have to insert these dash lines here, and what you get in the very end, you will replace tau that appears here with the transport time. So in a system where the scattering depends on the helper, you have a distinction between quantum scattering time and transport scattering time. So the momentum relaxation time and phase relaxation time. And all transport voltages contain transport time. So this distinction between these two is exactly coming exactly from this diagrams with the line, with the rest parameters. Okay, so just to summarize what we had so far, we discussed classical transport, and we had the Einstein expression for conductivity in terms of classical quantities like diffusion constant, and we have a diffusion propagator, which is also a propagator of the classical diffusion equation. It's here, diffusion propagator. And then I tried to show you how this same result can be derived from quantum mechanics in terms of the green functions, disorder average, and Hugo formula. Yes, yes.
As far as I understand, we took our quantum formula and somehow we derived classical, all the classical stuff. So in some sense, this is like semi-classical approximation, right?
I will answer the question on the right. Non-crossing approximation. Non-crossing approximation. Not equals.
Yes.
That's confusing.
Yes, this is exactly the question.
And if you want to include crossing diagrams, you will get some quantum effects that are beyond classical.
Yes, and that's the question actually, and why is it? Because it seems that our slope parameter is actually like strength of our impedances, right?
Yeah.
So why expanding over it is actually equal to.
Because we are considering situations when quantum effects are weak corrections to classical results in the same parameter.
Yes, but why our impurities are actually telling us that they are control all the quantum effects.
The Hamiltonian controls everything.
Okay.
Probably because our parameter contains H bar. I mean, each very charged H bar.
That's not so easy to tell because yeah, okay, well, H bar is hidden in many equations here. I'm not sure if you can trace it really to a single parameter, but maybe you are right.
This is because the Gaussian diagrams imply some interference or different scatterings in the disorder. That's quantum, that's why this.
Yeah, in a sense, yeah, when we don't cross the lines, we actually, I can draw many diagrams, and without crossing, you can always see that each green function connecting two impurities is always accompanied by a second green function, so it's always retarded advanced pair that connects impurities, which means that we consider not the quantum electron propagator, but like classical density propagator. So this is the reason how this approximation reproduces the classical result. Okay, I don't have much time left, so I will start a very new topic, but I will not finish it for you. And actually, this very new topic will be the part that I'm going to start. Will have much less equations, so it should be to discuss so the new topic once we have understood what the classical transport means and how it is described with the quantum mechanics. So the next topic is even theory of transport. It's actually it's already something about quantum thing, which is no classical counterpart. And it's very hand-waving. So the idea is the following. Imagine you have a classical piece of metal. This is a piece of metal. cube, and it has a size 8 Euclidean space. 8 by 8 by 8 by 8 by 8 d times. If it's metal, you can attach two contacts to it and measure its resistance. Or what people usually discuss is conductance. Conductance is inverse resistance. Conductance. So, for a piece of metal of size 8, there is a conductance, which is inverse resistance, and there is a conductivity, sigma, which is a material parameter, conductivity per unit length, whatever, cross section. So, conductance equals conductivity times the cross section. The wider is the sample, the better it conducts. Cross section is A to the power d minus 1. You have a d-dimensional object. In one direction the current flows. The cross section is d minus 1 dimensional. And the longer is the sample, the larger is the resistance, the smaller is the conductance. So it's also divided by the length. Or, if you like, it's sigma times A to the power d minus 2. This is how conductance of the metal depends on its size. And this is called, I don't know, Ohm's law. Ohm's law. And Ohm's law applies to metals. Now consider you have the same piece of material, but it's not a metal, it's an insulator. It does not conduct. You apply voltage, there is no current. Well, actually there is current, so there is an alternative expression, very approximate. The conductance of a piece of insulator is exponentially small. It's exponent of minus the size of the sample, just because it's a finite object, so some current can just jump from here to here. Tunnel through whatever. If you have vacuum, you still can apply voltage, you can have some tunneling and some exponentially small current flow, and typical length scale is psi is called localization length, but it doesn't matter for now. So this law is for an insulator. So there are two alternative formulas, one for metal, the other one for an insulator. And then there is a very big step which is called the scaling hypothesis. Scaling hypothesis. This is not a theory, it's a hypothesis. Some very smart people thought for a long time and decided that the derivative, not an derivative of the logarithm of conductance with respect to the logarithm of the size is this function should be a function of conductance itself, but not of the size. This, if this is true, if this derivative can be expressed as a function of g, if this is correct, it means that the system has this scaling unit. So the scaling hypothesis is the hypothesis that this identity exists. And there are some arguments why it should exist, but I will give in further lectures a more rigorous proof of it. Yeah?
Are we away from physics? Are we away from physics?
No, we are not. We can be away, we can be close.
I think it means that G can be any function.
Well, if G, look, if you have just a single function G of L, you can always do it like this. But now imagine you have many different samples of many different sizes, so you have many functions, G1 of L, G2 of L, G3 of L. And if all of them obey the same equation, this means that they have this.
So beta is the universal.
Yeah, to some extent should be universal. And but these two limits of metal and insulator is quite easy to calculate. So what I do, I just take this derivative. The logarithm of G, the logarithm of A. In the first case, it's just D minus 2 number. For a metal, it's just a number. And we see that the hypothesis holds. It's a number that depends on the dimension and on nothing else. It's very universal. So you can have any metal, you can have copper, aluminum, iron, gold. They all have D minus 2. And for the insulator, for this exponential function, if you compute this derivative, it will be just A itself. So log of G is minus A. The derivative is just A, and you can re-express the function of G as C, and it's log of G. This is what it means. This is also quite a universal function. It doesn't contain any material parameters. Psi, for example, drops out from here.
So this is limits of big and small g.
Right. So we originally assumed that the system, which is a good metal, has large conductivity and G is large, and insulator has exponentially small conductance, G is small. So in a sense, if this hypothesis is correct, there should be some function beta of G which behaves like this large values of G, and like this small values of G. So, as you correctly pointed out, this should be true for large G, and this should be true for small G. And the board still doesn't move, so I will put here. This derivative d log G by d log A as a function of, let me do log G on this scale, is d minus 2 when G is large. Somewhere here, we have d minus 2, which is just a straight line. One straight line, second straight line, and third straight line. This is for three-dimensional case, two-dimensional case, one-dimensional. So d minus 2 is 1, 0, or minus 2. And for the very small g, when this logarithm is negative, that's number here, this function should be just a linear function. And if the scaling hypothesis is correct, there should be one universal function beta of G that connects these two limits. So it should be something like this. And again, if this hypothesis is correct, whenever we have some sample, some material, some conductance, so we know it's conductance. For example, we have a three-dimensional sample of, this is not a metal, but imagine I take something like this, I measure the conductance, and I say that I somewhere here. So it's a three-dimensional object, and my conductance is this one. And I say that the derivative here is positive, which means that if I start to increase the size of my sample, some material, I increase the size, the conductance grows, so I move this direction, and I end up somewhere far in this infinite dimension. And if I have a sample, and its conductance is somewhere here, when the derivative is negative, I start increasing the size of the sample, derivative is negative, so I go in the negative direction. So the point where this function crosses 0 is the phase transition point between what we call metallic state and what we call an insulated state. And this is the Anderson metal insulator transition. Yeah.
Does this all work for sigma for only the diagonal elements, or is it just for any subtype of that?
You mean this sigma?
When we write on flow, we write it for the sigma alpha, right?
Okay, this is, in a sense, this is a conductance in one dimension of the cube, so it's the same sigma.
But will this kind of reasoning works it for other parts of the
Yes. I mean, you may have some strangely non-isotropic materials which have different conductance in different directions, but then you should, oh, this is not what you asked.
I mean, things like Hall effect.
Oh, no. Hall effect is beyond this. Hall effect we will discuss later, it's different. So for now, this is just for the usual conductance, without any magnetic. So once again, there are two, so to say, not states of matter, but two types of materials, metals and insulators. In metals are not the material that has zero resistance, it has finite resistance, but the point is that when you increase the size, it reaches some finite conductivity per unit length. And insulator is something when you increase the size, the resistance goes to infinity. And there is a single point which separates these two things, so you can have many materials and you can always classify them. These are metals, these are insulators, just based on where you are on this diagram. And what this thing also suggests is when you consider two-dimensional, one-dimensional materials, they're always insulated. I mean, this function is negative into 1D, so presumably, there are no metals in one dimension in the sense that even a very clean system, two-dimensional, when you start to make it larger, eventually will become useful. This is all based on the scaling hypothesis. I gave you 0 grounds why this hypothesis should be correct. So for now you don't need to believe it. But actually later lectures I will kind of prove it. So this is actually the correct thing, and this is how our nature works. And with this I will end today's lecture after answering last questions. Sorry?
We said that here we can only have insulators for very large L.
No, this is not what I'm saying. I'm saying that the definition of what is the insulator is the material that becomes more and more resistive with increasing the size. So if you have some small piece, you can measure the resistance, it's fine. If you don't know if it's a metal or insulator. To distinguish, you have to see how it changes. Any other questions?